Hello, my name is Gregory Kenning, and I go to the University of Pittsburgh. My PI for this summer is Dr. Legravrand at Texas A&M University, and my project for this summer is using recursive neural networks to account for history effects within materials. I'd just like to thank the NSF for funding this project. Without their support, this project never would have been able to come to fruition. So, what's the purpose of this project? Well, in the past, AI has been used to model material progress through progressive stresses and strains. However, all of these AI models that have been created so far have all lacked one key feature, which is memory effect. Memory effect is pretty much the idea that as a material progresses towards a certain point, it can take different paths. Let's say it has a different yield strength at different points because it's been affected in the past. It takes these different paths, and in taking these different paths, usually it results in a different outcome because if it takes a different path, it results in different yield strength, which can affect how the material progresses over time. Now, we propose that instead of using a basic neural network or a basic AI to look at these features, we instead use something called a recursive neural network, and a specific type of recursive neural network called a long short-term memory neural network, or an LSTM. We can consider a material's history using this. Hopefully, we can consider a material's history in our prediction while taking advantage of AI predictive capabilities. We will do this by using PyTorch neural network software to create a model that should accurately predict the mechanical responses of materials using deformation histories. The main paper that we're referencing in a lot of our data and such is the Shabashh paper that is referenced here below on the right. Now, a basic introduction into what neural networks are and recurrent neural networks are and how they work. A basic neural network, which is a lot of basic AI, all it does is it takes an input, it runs it through a dense predictive layer, and that produces your prediction output. As you can kind of see in this process, there isn't really any kind of input for the history of the material. So it doesn't matter what the previous steps were and how they may affect the material. This doesn't even take into consideration whatsoever. Whereas recurrent neural network takes both an input and a hidden state input as well. So two different inputs. The hidden state input is kind of the summation or the amalgamation of all previous states, which allows you to factor history in for your material's effect. So then again, you take this input and this hidden state input, and you run them both through a dense layer and sum them together. This creates your new hidden state for your next run so that your next run also has some kind of history effect that includes this current input. Then you take that hidden state, you run it through one final dense layer, and that produces your specific prediction for that specific set of data points, right? However, again, the issue with basic recurrent neural networks and why we're using an LSTM is that basic recurrent neural networks, while they do a factor in for memory, they kind of tend to collapse when it comes to long-term memory. Where LSTM, which is specifically long short-term memory, can much more easily factor in longer and shorter term memory, which means that after longer and longer runs, like runs in the thousands of loops, you're able to actually produce values that how should I put this? You're able to produce values that actually stay consistent with your prediction rather than go completely crazy. So, as I was saying earlier, we use the Shabashh paper as a reference for a lot of our data here. We took most of our primary data from this graph in the Shabashh paper. This graph is the progressive strain of steel 316. It is from a untouched steel 316, so it's not affected by any kind of previous prior conditions. And this is kind of what we use to train most of our models. This paper, while having our data, also has two pieces of crucial information. The first piece is it shows the experimental results of how prior strain relations can affect stress strain conditions, which again is a great source for us to compare our final results of our AI to an actual experimental result. And within the paper it has its own predictive system, which again is a really nice comparison point for us to be able to compare our prediction to their predictions within their paper. So, the methodology of our paper. Our plan was to first develop a RNN model that kind of just uses PyTorch and simply looks at loops based off of training data and predicts what the next loop might be. There's no pre-existing conditions, there's no physics. It just looks at a loop and predicts what the next loop might look like based off of the previous data. Then we want to add another component so that the predictive measures here can factor in kind of different inputs. So if we have a different pre-existing condition or a different history effect, it could factor that in and produce at least a slightly different output for each one, we're hoping. Finally, our plan was to add physics to the model so that any predictions can be properly compared to actual experimental data that actually has, well, the physics in it, right? So, our results so far. So the first thing we did was we took an existing neural network that we found online, which was a text prediction neural network, and we used it to predict the numerical data of our system. We switched it so that it would predict numerical data within the system rather than text data. Then we adjusted it so it predicted a range of points rather than a single value. So instead of producing a single output or average to a single point, it averages to a range of points, or in our case, a full set of loops. Then we set it so that it's able, again, to predict, instead of training off of text data, it trains off of stress-strain data, so we're able to actually predict stress-strain loops. It was at this point in the project where we actually switched to an LSTM model. This is because at this point in the project, our runs started to get a little larger, and that was when the basic RNN started to collapse a little bit, so we switched over to something that would work for longer and longer runs, or the long short-term memory system. The next thing we did was we set it so we could factor in pre-existing conditions. And after we did that, this resulted in the model on the left. Again, as you can see on the model on the left, it's not super accurate, but it is able to produce a stress-strain loop that at least is vaguely, well, maybe not accurately, but vaguely taking on the shape of the numerical data, which is kind of a good starting point for us. Then came the physics implementation within our system. We had three main basic parameters for our physics. First was the Young's modulus and the initial conditions of the material, just so we could kind of compare our, once we implemented physics, once we implemented the physics, we could compare the physics and the initial conditions directly to the experimental data so that we could see at least the physics is acting properly. And the next two things we added were the nonlinear kinematic hardening and the nonlinear isotropic hardening. The kinematic hardening is pretty much as stress-strain loops continue to progress, they tend to shift, and isotropic hardening is that as stress-strain loops continue to progress, they tend to expand or get bigger. The nonlinear aspects of both of these pretty much just states that instead of these, we set up our equations so that instead of these loops going off, expanding off into infinitely big systems, or just shifting off to infinity, they kind of cap off at a certain point. The physics of these three basic parameters, along with our initial training data and our initial conditions, resulted in the predictive model on the right. As you can see, it expands like our training data did. It doesn't shift much because our training data also didn't really show a whole lot of kinematic hardening. It showed a little bit, but it didn't overly show it. So this actually models our training data pretty well. And while our initial conditions aren't exactly implemented here to the fullest effect, this is at least a good implementation of, and proves to us at least, that our training data and our physics is working properly within the system. Now to our current final model and the actual implementation of initial conditions. So in our current model, what we did was we took two different paths, so two different histories that go to the same strain and stress, which is 3% stress at 260 megapascals. And as these take these different paths, you actually notice if you look closely at the graphs here, they actually go to different extremes. For example, the model on the left goes a bit past 3% strain on both sides, whereas the model on the right doesn't actually pass 3% stress or strain, which proves to us that in conclusion, our LSTM so far, after implementing all our parameters, including our physics, our initial conditions, and our training data, with the implementation of different histories, actually does produce at least slightly different outcomes, so we can confirm that our model currently does change depending on materials history. So our next steps within this is to compare it to the system produced by the Shaboshed paper and the experimental data produced by the Shaboshed paper to get and to narrow it down and to refine our model so that it is able to produce an even more accurate estimate. Thank you very much. My name is Gregory Kenning, and this has been my project this summer.